So system design is not just for developer or architect. It is for everyone who is building scalable and maintainable application for a global audience. Why do I need to understand about distributed system? At the first place, right? So in order to build a application which is used by a large number of user on multiple devices like phone, tablets, or desktop, or you want that your application becomes gradually scalable as demand increases or the user reduces, it stops using more computation. We want that dynamic scalability in our application, right? And also we don't want our application to crash due to overcrowded or when there's high traffic in the system, which might cause single point of failure. So that's a reason we need to understand why we need our application to be distributed. So distributed system is mostly about how one system communicate with other system. So at the core of it, we know that we need to send a message over network, and and to transfer this message from one network to another, we have a lot of technology or keys that we need to consider, like what protocol we use when we transfer, how are data received from client to server or from data loader to API gateway, and what happens when network fails, like how do we handle outrages, right? How do we even prevent eavesdropping? Like are there any technology, are there any protocol that can prevent a third person to eavesdropping into the conversation, right? For example, TLS encryption is one of those. So another core idea that we must need to understand regarding distributed systems should be coordination and consensus algorithm. So when two nodes communicate each other, they need to decide onto something, right? They need to come into an agreement, right? So to make that agreement, there has to be a coordination among them, and they follow some algorithm such as concession algorithm to make the nodes agree even when one of the nodes fails, right? For example, you have three nodes, right, in your distributed system, and one of those fails, and so you do not get a majority vote on deciding what it does, right, and what it has to do on the update that user made. So in that case, probably the raft and jab algorithm can come into play to make the consensus on what they need to do with the failure. So the thing that we need to understand in distributed system is we cannot avoid failure, and it's a norm. We have to deal with it. We have to go as it fails. After the network failure, there's only two things that we can decide. Either we can follow on consistency or we can follow on availability, and that's the core idea of CAP theorem. So CAP theorem says that we cannot really avoid network partition, and in case of network partition we have to make a favor of our consistency or availability. So and there are other distributed coordination and coordination has to be performed, like distributed log, right? Clock algorithm is there where we decide how do you coordinate between what time two node are stored in two different geographical location, right? In that case, each one has different time local timestamp, so we cannot really rely on the physical timestamp. Rather, we need to follow on some logical timestamp. So that is something we have to understand when we are understanding about coordination and consensus algorithm. So now we will discuss about another core principle of distributed system, which we define as a scalability. So in scalability, we generally deal about growth, the growth of data, growth of user, or more requests from the user, without degrading the performance of the entire system. So generally, when the few unit that we take consideration on scalability are throughput, latency, and capacity. So in throughput, we need to understand how much time each request is processed, like how much time it is taking to process a request, right? That's a throughput. Our target is to maximize the throughput. Okay, so we need to maximize more requests processed per second. To do that, we need to improve our latency. So it meaning that we need to reduce the time taken to process each request or single request. So it's called latency. So the capacity is that at what maximum level the system will perform in its good state without starting a degradation. So throughput means process as many as requests in per second, whereas latency means try to send a request as soon as possible, like improve the time processing those throughput. Yeah, and the capacity means simply the system has its upper limit. Until then, it's okay. Otherwise, it will just start degrading. So, in generally speaking, in scalability, we talk about vertical scaling, horizontal scaling. So, in vertical scaling, meaning like you have a server, one standalone, you increase the CPU performance, you add extra core GPUs or memories, right? But it has some limitation. It cannot go, it cannot explode, meaning it cannot go far beyond what a system can handle, right? So that has limitation. It's more expensive in compared to horizontal scaling. Horizontal scaling is more like scale out, where we add multiple systems in parallel with the previous one, and this is one of the most preferred way of building your distributor system. You've seen that horizontal scaling with lower cost efficient lower cost machines or a single system has a higher advantage than the vertical scaling. We need to look onto other component in our distributed system for scaling purpose. Like we need to see database scaling, where we need to implement replicas, sorting, and caching layer, so that we can decrease the latency and improve the latency and process and have a higher throughput. And the other way of improving scalability is having asynchronous processing. So offload heavy processing queries or requests into a queue, and when the system is available, we process that. So these are some strategy of handling growth, basically handling scalability in distributed system. So as per CAP algorithm, network failure or network partition is unavoidable. Or in a distributed system, we cannot really avoid failure. The failures are inevitable, meaning that we cannot avoid. But the thing that is good about distributed system design is that we need to make a plan how to handle those failure. We want our system to be available all the time, but that's not possible. No. So what we need to do is we need to plan for the failure, and that planning out of failure can be handled by using availability techniques, right? So availability is generally described in number of nines. Let's say you want 99% of availability. That is two nines, right? So in that case, the downtime per year, meaning like the system can fail for only 3.65 days. That means only 7.3 hours per month. And if your service is committed to have 99% availability per year, that means not available for 3.65 days. The only acceptable downtime per year will be 3.65 days. If it goes beyond that, then that's the issue. Then it's not 99.9, it's not 99% of availability. Similarly, if your service says or if your service supports 99.9% of availability, meaning it has three nines, then the downtime per year is only allowed for 8 hours. Like in a year, just 8.76 hours. And for a month, you can assume it's just 43.8 minutes, right? And if your system says uh, it has 99.9% of availability in a year, that means your system fails just for 52.6 minutes per year and about 4.38 minutes per month. So, and if there are five nines, you can think about 5.26 minutes downtime for your service, and only 26.3 seconds are allowed to be unavailable for a month. And there's another way we can make our service available and resilience for is by using this all technique, which are redundancy. Like eliminate what do you mean by redundancy is that we keep multiple server available, and yeah, so that if one server falls down, another server uh, plays the roles of the failing servers, right? So it's eliminate the single point of failure because it has multiple instances on a multiple reason. And similarly, what we can do in a database side is that we can have multiple replica of our database or of our services user database, right? And it is copied into multiple what do you say servers, multiple instances. And if, for instance, a server crashes down, there should be a failover technique which will automatically switch to healthy node when failover occurs. And those failed, those failed servers should have auto restart services. So when those failed services gets time, it is itself healed and it come back to the network. And there's another technique that generally used some chaos engineering to build our services resilient, fault tolerant, and available most of the time. And this observability and operation is one of the most important technique that we need to understand, because you can't fix what you can't see. So if you can't observe what was a failure and how the failure happened, we will not be able to find a solution to fix it, right? And we need, for that we need to log all those failures. We need a metrics to calculate what kind of risk it associate with, and we need a traces. So these three pillars of observability is important when we are building distributor system. Other operational excellence that we can provide is using alerting system, and documenting the common procedure for common incidents and postmortems. So in the consistency model, it defines, right, how and when objects become visible across all nodes. So, but it's a fundamental trade-off. Why I say is because you every application has different way of handling consistency. For example, so when you are dealing with banking or inventory related services, right, or application, you need strong consistency, because we need to have like every user should see the same data at the same time, right? There cannot be inconsistency in the what one user from one geolocation sees with respect to other person in other geolocation. And when it and that's a strong consistency. And when in an application like social media, DNS, right, where the delay in consistency is okay. One user geolocation can see the data a little bit late than the other geolocation or other countries people or user. So when there's an update propagated, eventually temporary inconsistency is allowed. So that is what eventual consistency means, because we will get the consistency, but eventually after few seconds or few hours. What is casual consistency? So it maintains the order. Uh, uh, yeah. So on a collaborative editing, you need like casual consistency. So this is all about consistency model. So far we discussed about fundamental skills that we as a developer must understand to build our software. See you in the next video. Bye.